right there. And I want to talk a little bit about how we use an LCD display. Unfortunately, it's a lot more complicated that there. And I was going to look for it here. Let's see, HD 44. Let's get the right part number here. HD 44780. And hopefully I've got internet here. I meant to download this data sheet before I came to class. There. Oh. All right. Let's try this again. Okay, there we go. All right. Did I start my recording yet? Yeah, I started my recording. Okay. All right. The most common display that there, and I didn't order a lot of. I only ordered like I think six of the displays because my guess is when we do that lab, we'll probably work in larger groups. That they're in, and I'm hoping that I got the right ones. That's the other reason that they're. But when we look at a display, right there, you can see our our internal workings of a circuit that there is almost as complicated as the 8051 itself. Right there, it's a fairly messy looking display. That there. So as we look at that there, and typically we're going to be going through that there. We can use this either in 4 or 8-bit mode. With our processor, we're going to use it in a 4-bit mode simply because we have a limited number of pins that there. So Hitachi is the manufacturer of them, the data sheet, but there's hundreds of companies that make these same ones. Matter of fact, I ran into quite a bit of that there. And they actually have a microcontroller on the chip. If you look at the display chip, you can see it's a much larger chip than our microcontroller, right there. So, but it's all built into the display unit itself, right there. So, and I'm not going to go through this data sheet. I'm going to post a link. I'll put it up on Facebook. That there. But these instructions I'm giving you that there, and as you can see, these instructions is 60 pages long. The data sheet for this particular display. It's not quite as long as the 8051 data sheet. That was 280 some pages. That there, but there are some important there is some important information in the data sheet on how to interface to it. Fortunately, there's all the characters that it generates. That there. Fortunately, the textbook that I put up, I did put this textbook up, didn't I? That there. It should be up there. If not, let me know. It's the one by the woman that there. Chapter 7 talks about how to program the LCD, right there. Now our pins will be different, and we will be using the 8-bit initialization. That there, I have code I'll post for that when the time comes. So I just want to kind of go through this here, that there, and then we'll talk a little bit about analog, right there. So as we look at this right here, we jump to the section on the display. Right here, and as we look at our display right there, the interface to it here shows 8 data lines and 3 control lines. We're going to use 4 data lines, which involves a little bit more work because we have to write the data half a byte at a time. But as you could well guess, if we're going to interface a keypad at the same time, the keypad requires 8 lines, right? Because we need 4 columns and 4 rows for the keypad, so we need 8 lines for that. And then if we use the LCD, we need another 7 lines. That takes us up to 15 lines. And if we're going to read an analog port, that requires another line. So that's pretty much uses up the full power of, I/O lines of our microcontroller. If we have a very simple temperature control, and we also need some type of output right there, so we can have another line for an output right there. So as we look at our particular microcontroller, we've got a limited number of lines available. So if we're going to do any kind of project interfacing to it with an LCD and a keypad, we have to operate it in that there, because otherwise this requires 11 lines. I'll have to look at it a little bit more carefully right there. But the keypad right here, the keypad the display we're using is a 2-row by 16 right there. So right there. So you can get different sizes of displays. You can get 4 lines by 32. You get 4 lines by 80. 8 lines by 80. You get all kinds, and they all use a very similar interface right there. So the ones that I ordered are a 2-line by 16, just as described in this book right here, right there. So as we go through and look at this, the display RAM in the display is actually 40 characters, hex, right there. So it's fairly large. If you look at 40 hex, that's, I can't even think this morning here. Program hex 40, that's 64. So it's 64 characters wide right there, of which 2 rows of 16 are available. So our display, actually, we can load it in and we can move what's displayed along. And a lot of you have seen those rolling displays that as it moves one character at a time. That's how they're doing that. They preload the RAM and then they just change the start of the display right there. So the characters in the first row start at 40. The second row starts at, first row starts at 0. The second row starts at 40 hex right there. Right there. So this is in the display DRAM, and that's where you can set any address that you want. The simplest approach is to leave it at 0, 0. In other words, we just load everything at 0, 0. The character controls the display defined characters. You can go in and you can change the character set however you want. You can display unique characters. This particular text does not go into that, and I'm not going to go into that. That's a fairly complex. If we went back to the data sheet, where is my data sheet? Nope. Maybe I closed it. Oh, it's right here. This is our display RAM right there. So as you look at this right here, these are all the various characters. You can go in there and modify those characters if you want. That's there. And you can see we've got a lot of characters to pick from, all the standard letters, but if you wanted to try to come up with some type of if you want to come up with a custom display that would display Jawi, for example, or Chinese, assuming you can generate Chinese characters with that there. Now, actually, because Hitachi makes it, it does have the Japanese in there. So, but it doesn't have Arabic or characters in there. So, if you wanted to come up with a custom one that would display Arabic characters instead, you could do that. Again, we're not going to do that. Talk about that there. So, we have our pin definitions that there. you can operate this thing all the way down to 2.7 volts, which is good because our particular board actually operates at 3.3 volts. Again, this discussion here uses 11 lines. We're going to use 7 lines. Right there. So the only difference is the number of data lines right there. The data is bidirectional, so we can read the microcontroller right there. Right there. So there, with any, you don't want to use that there. So that there, you write FF to a data port before trying to read it. Right there. That's how you read the data port. You don't enable the push-pull outputs. You use the weak pull-ups and you write FF to it, and then that there we talked a little bit about that there. So this is the pins on the microcontroller or on the data that there. I wish I had one to show you that there. That there. And let's see. Let me HD. I don't want to look at the data sheet. I just want to look for a picture of one. Okay, this is right here is a good. This is what it looks like right there. This is what it looks like right there. As we can see, looking at it, we've got BSS, which is ground. We've got plus voltage, which is called VDD, which is our 3 volts or 5 volts or whatever you want to put on that there. We got our contrast voltage. That is normally connected to a potentiometer where we can adjust that there. We may leave that float, or we'll have to put a potentiometer on that there. So that there, we got register, select, read, write, and enable. Those are our 3 control lines, right there. And then we've got our 8 data lines there, which we can put it in 4-bit mode and only use 4 of them, right there. We've also got our backlight that we can turn on or off. We can have a backlight on this right there. So this is what it looks like. And everybody's seen LCD displays that there's something unique, but that shows what it looks like right there. So these are the various lines that we have here. Again, these are our 3 control lines right here. Right here. Enable, transition low to high. The LCD reads the state of RS and RW. RS is whether we're writing an instruction or writing data. And then RW is our read-write line. It's a 0 to write. It's a 1, so it's a read/W dot, the way you normally would write that. And then we've got our data lines. So those are our 3 control lines that we use to control writing data to the display, right there. So right there. So we have to initialize this thing first. This is our instruction set for this thing. Right there. As you can see, it's a fairly long instruction set there. Right there. We can write right here, and there are some times here that we'll talk about. To be honest with you, these times are somewhat manufacturer specific. They're not guaranteed to be right for this particular microcontroller. Every one you've had. I actually designed a system around one of these that there. We got we ordered, what was it, 100 from the manufacturer after the design was done. They came in, none of them worked. None of them worked. And what we discovered was the timing on the LCDs they used a cheaper LCD versus the one that I used in the lab when I designed it. So when they came in, so we had to go through and we had to reflash all the all the prototypes that there. So we built 100 of these things to put them out in the field to test them before we went into full-fledged manufacturing. And it was a good thing we did only build 100 of them, because we had to reprogram all 100 of them. That's there. And fortunately, when we did the design, we put the programming head on, the little thing where we could plug in and reprogram the device there instead of having it programmed in the factory. That's there. So we could reprogram them in the field. That's there. So, and after that, we decided to leave that on before we were going to not put it on when we went to full-fledged production. That's there. This was a device for measuring what was that the system used for? It was the GeoFlow project. It was for, you wouldn't have it in Malaysia, but some people heat their homes by pulling heat out of the ground. They run pipes underground and they run water through it. In the wintertime, it's warmer underground than it is on top, so they would partially heat the water by running it through the pipes underground, and then they would heat their homes with heat it a little bit more, and then run it through the house to heat the house. But it was called a geothermal heating system. It was for controlling that there. So, I designed the project, but it was one of many that I've designed. I couldn't remember which project it was that had the problem with the LCDs there. So, but I did run into issues, and I will say that I've used this display probably on about a dozen different design projects. So I've used it multiple times there. And this particular project, we were using an 8051. No, we were not using an 8051. We were using an HC12 or HS12. We were using a Motorola chip at the time. So So it wasn't a 8051 project that I had trouble with, but the code is the same because we're writing in C. So what processor we use really doesn't matter. There. So again, we go through here, and basically, if we want to clear the display, we look at any transition on the enable line, because if you look at the enable line right there, a transition from low to high, the LCD reads the state of RS and RW there, and a transition from high to low, the LCD controller reads the data bus. So it takes a full pulse for the LCD to read anything, because on the rising edge it reads the RS and RW lines right there, the control, the two control lines, and then on the negative going pulse it reads the actual data that's there. So it takes two lines for things to happen right there. There's two transitions. On the rising edge, it figures out what it's going to do, and on the trailing edge, it actually does it right there. Because remember, RS tells the LCD whether or not it's going to be an instruction or something to write the data, and then the RW is whether or not it's a read or write instruction right there. If it's a read instruction, that means that it's going to take and put the data out there right there. So when you look at this E here, you see the plus, the up down. So that means that it's going to read 00 is that it's going to be instruction. All these instructions, you'll notice, are 00 until we got to write to RAM and read from RAM. That's there. So and we would set the addresses ahead of time. That's there. So as we go through here, so if we want to clear the display, and also I should note that all the instructions only use the lower 4 bits of the data bus. Otherwise, we could not operate this thing in a 4-bit mode right there. So as we go through the instructions, we got clear, which is 1. We've got return home, sets the DD-RAM back to 0 and returns the display to the original position if shifted. The entry mode sets the cursor and display will move when data is written to it. So we will either increment or decrement that there. So as there sets the cursor and display will move when data is written to it. So basically all that means is that it moves the cursor to the next location. And we can either write it right to left or left to right. That's that decrement or increment right there. The normal is increment, where we write to position 0, then we write to position 1, we write to position 2, we write to position 3 up there. But we could set it to where we could start off at position 40 and go backwards, or 39 and go backwards if we want to. Up there. So there, and then S1 it shifts the display, whether you want the display to shift right there. Display on or off controls whether or not it's visible and whether or not the cursor is blinking or not right there. Turns the cursor on or off right there. The display or cursor shift moves the cursor or shifts the display. Remember, I said that we can shift that display across right here. So that's how we would shift our display right there. So moves the cursor or shifts the display. So one command does either one or both. If it's 1, we're shifting the display over, and if it's 0, we're just moving the cursor. And we could shift left or right there. Right there. And function is that we can say that we want to have it in 8-bit mode or 4-bit mode. This is how we program for 8 or 4-bit modes. The number of display lines and the character fonts that we have right there, whether it's 5 by 10 or 5 by 8 in terms of our size set there. Set the CG RAM address right there. So we're not going to do much with that. Set the display address right there. That's how that's where we determine where the next character is going to be set there. And then we have our busy read and write flags right there. So these are all the instructions that we need to have to write to operate the display right there. And then we write to RAM or read from RAM. So we can either write to the RAM or we can read to the RAM right there. So there, and notice that we've got write data right there, writes to, and again, as we look at our control lines right there, we will normally write to our display RAM right there. Right there. Right there. Where do we set the address? Character right there. Okay. We'll look at the code here in a few minutes here right there. So we've got some code here that goes through here. We're not going to go through it in great detail. I am not going to require on the final exam that you be able to write this code. That there. We'll use the code that's given. We've got LCD character right there. So we've got an LCD busy wait. All that does is simply waits till the LCD is not busy. We set the control port there to RS mask. We're going to set RS to 1, and we're going to set RW to 0. That's our two control lines. So we're going to set that to 1, 0. 1, 0 is write to RAM, right there. And then we're going to then write to our data port the data, and then we're going to pulse E and then return back 1. It's a very simple command to do that. That's how we write a character. Right there. And then here's our command. We pass it a command. Again, we're going to put RS and RW to 0. We set the data to command, and then we pulse E right there. So actually writing the code is fairly straightforward right there. So we have to do some things first here. Now again, we set these masks up right there because those are the control ports. In this particular case, we're putting the control port on port 6, and our our data port is on, or our data port is port 6, and our control port is port 7 on this code. We don't have a port 6 or port 7, so we have to modify this code to use it right there. We've only got a port 0, 1, and 2 right there, and I think we only have part of port 2 right there as we look at that there. So we look at the pulse E, we just have a small, that there. We can, since we're using ports 0, 1, and 2, we can actually make this simpler. We don't have to use this OR command, because this OR command right there, what this line here is doing is it's setting that bit to 1 by using the OR command right there. And then we're setting to 0 by using the AND command with the NOT mask. In other words, we're setting that to 0. So we're using the OR to set a bit and the AND to clear the bit. We could just use set bit and clear bit in our case right there. So our code will be a little bit right there. Synchronization is actually quite slow to process the command relative that there. So we have to put delays in there right there. So we also have a function here that's called LCD busy wait right there, and this is, we're waiting for LCD port, data port there, so we have a delay, wait for the busy flag to drop right there. And there's the busy flag right there is the highest bit right there. Right there. So we're waiting for that to be cut there. So these are just fairly simple functions right there, just to simply wait. That there. We have some other functions. This is the one that's the most complicated, and we have to change it right there. Actually, we're going to have to change it, a number of these functions, because we're going to use it in 4-bit mode. You know, I'm going through this, but the real learning is going to be when we actually get the LCDs and we start programming it right there. But basically what we're going to do is reset RS, RW, and E to 0. We have a very large delay right there, 16 milliseconds. We set that LCD data port to 38, which is the 8-bit mode. We will change that. We pulse E. We have another delay. Again, we pulse it to 38 again. And then another delay, we pulse it again. We have to write to the data port 3 times the instruction. And as I said, it's just one of those things that you just have, that it just requires. It's in the data sheet that you do it. That's there. If we pull up the data sheet for this, and I'm not going to go through and find it, but right there they have a somewhere they have the initialization routine right here. They go through all the registers, pin functions. There's all the pads. We don't need to worry about that. The controller. I thought they had the initialization routine right there. It may have be a different data sheet that I saw. Right there. Up there, DB0, busy flag, display RAM. Up there. Again, you can see that we can display various positions right here. We shift to the left, we shift to the right. That there, that just simply changes the code or what's being displayed right there. Character generator. Right, ROM. Program pattern. Evidently, they don't give the. I thought it was right at the end. They gave sample code toward the end. This is showing the example. 4-bit operation. Reset function. Instructions. That's the same instruction set that we just went through. That's where it came from. Clear display, return home. A little bit more detailed. Cursor shift. Right there. Busy flag. Read data. Interfacing. Right there. See, this is showing connected to an H8 single chip mode. This is connecting to a different processor. I'm not sure which processor that is. That's not one I've ever used, HMSCS. Right there. It's probably a Japanese processor. Right there. Showing the various connections there for that. This goes to 4-bit. And as I said, these data sheets don't make it easy to find things. Okay. Yes. Again, they're showing here. You see. And I lost my mouse. Oh, there it is. Okay. Yeah, right here is where they're showing. This is what I was looking for. Here they're showing that you have to do it 3 times. Wait, power on. Wait for more than 15 milliseconds after it's powered up. So that's your initial wait for the 60. They had 16 milliseconds. Write the instruction 1 time. Wait for 4 milliseconds. Write it again. Wait for 100 microseconds and write it a 3rd time. So it's right there. It's in the data sheet. As you can well guess, as a first-time user of this particular display, seeing how this is on page 45 in this data sheet, it's not real clear that you have to do it 3 times. You have to read the data sheet all the way to 45 to find out how you actually connect this up right there, and then you end the initialization right there. So that's the initialization routine right there. This is it. This is the way that it's done right there, is that, again, the instruction that we're putting is 38. That puts it in 8-bit mode. We would change that to put it in 4-bit mode. And we power it up. We set, that there. We wait 16 milliseconds before we do anything. We write the 38. We wait 4 milliseconds. We write the 38 again. We wait 1.5 milliseconds. We write the 38 again, and we wait 1.6 milliseconds right there. Again, it doesn't. I don't know why this says 1.5, 1.6 right there. And what I've discovered is that if you look at that data sheet, it gave times. These times are different because obviously they probably use a different manufacturer, that these times are change. Right there. This is the routine that got me into trouble with that one design. And trust me, my boss was not really happy when we had 100 units at about. These were initial prototypes, so we were, the actual production cost was only going to be like $100 a unit, or about $80 a unit. But these prototypes cost us about $600 a unit because they were one-time, a very small run. That there, and when all 100 of them didn't work. That wasn't a very happy day. That there. So obviously I stayed up fairly late into the evening before I figured out how to get it to work, and then we had to go back and reprogram them all. But at least we were able to fix it right there. So But that's how you initialize the display right there. So now if you do it right, that they're using the display is very easy right there, because once you initialize and have all the code to write to the display is just as simple as using printf right there. So it's a fairly straightforward, this particular program here, all it does is sets a counter equal to 0 and just keeps incrementing the counter. That there, you can see that there. So once you set the display, printf is how we write to it, right there. So a lot of this, and where am I at here? Oh, I'm toward the end of the project right there. But we have to have a number of functions to write to the display. And as I recall, the ones in this book did not work right. I've got functions that do work right there. There's some monkey that there. We've got some LCD software that has to an option is use the 4-bit mode that there. Use 7 that there. It's a little slower, a little bit more complicated because we have to transfer our data 2 bytes at a time, or 2 nibbles at a time right there. So again, this is the instruction set. Where was I? I lost myself here. I covered that. Okay. This was the LCD load command. Okay, I covered that. I was just going through their synchronization. The busy wait I covered. This is the initialize. We just covered that. And then once we've got that done, there's some other functions that need to be written right here. This is the main, and then this is LCD go to character. After 64, we'll wrap around the second line, eventually overwrite the first line. This is a go to that tells it where we want it to go to on, as far as on our display, right there. That's a function where we load command and we give it the address. So if we want to go to the second line, we'd say LCD go to 0x40. That's the first character of the second line. If we want to go to the first line, it would go LCD 00. If we want to go to position 20 hex, we would go to that there. Remember, we've only got 16 characters, so we can only. You should not go to anything but to 0x0f would be the last character, or 40 to 4f. That's what our display will show right there. We've only got 16 characters, unless we move the display, shift it. We'll keep life simple. All right, the next thing right there, let me kind of go through here a different set of slides on this right here. Oh, here it is. Okay. Now, if we go to, first off, let me kind of go back to where was it? Oh, here it is. I went through this. This is the page I gave you for the matrix keyboard. As you recall, we went through this last week. If you look at this particular display here, they also show the LCD right there on that there. So and if you go through the code, we did not talk much about the LCD, but this is putting LCD on ports 0 through 2. Port 0 is the control lines right there. Where's the E? Oh, there's enable. Where's RW? They don't show RW on this one here. Do they show it connected? Yeah. They show RS. RW goes. Oh, they're okay. They're grounding. They're grounding the RW line because they're always in the write mode. So that's one way of saving a pin, and we could do that. Except for the fact that I think if you use the code that right there, if we use that code from here, LCD, they use the RS for LCD bit, the RW, yeah. If you use the LCD busy wait, then you have to do that. That's there. If you just simply put a long delay and you assume that the LCD is ready whenever it's supposed to be ready, then you don't need to do the LCD wait. Then you can save one pin. So that's what this particular website has done. In their code, they've actually saved this line right here, this RW. If we follow it through, the RW line is brought here to ground, so it's not connected to the processor. Right there. And going back to this is a typical display, and this is the one we're going to be using. And this particular website, and I'll put the link to that there. This is using, again, for the 4-bit mode, this is the connection that they're using right there. Obviously, we're going to have to change those because we don't have port 2 available, the upper end of port 2. So we'll find which lines that there when we connect that up. When I write the lab up, I'll sign those pins, because what's going to happen is I'm going to have to get the LCDs in my hand. I'm going to have to make it work, and then I'm going to have to give it to you to make it work. But before I give it to you for you to do it, I have to do it first. And I can't do that until I get them in my hand, right there with this board, that there. So they've been ordered from China. So whenever they show up, that there. Hopefully last time I took about 2 weeks for them, and it's been about 2 weeks. I expect them any time up there. So okay, there's a bunch of functions that are called right here. This is the main code, and if this code here actually works a little bit better than the one in the other book right there. But this is the 4-bit mode right here, and this is, again, here's our 4-bit mode. RS is port 0, port 0, bits 0 and 1. Those are our control lines. Our data bits are on ports 2, bits 4 through 7, the upper half of that there. We may use just the lower 4 bits of port 2. That would be the only change that's there. And what you have to do then, in order to this sets the cursor to 1 1. And again, there's a function to do that. I'll go through that function. We have a function here called LCD for write string. So instead of using printf as the other one does, we use the function LCD write string right there. So that's our main code that there. We just go from character that there, and we just shift it left right there. Right there. And then we shift it back to right, that there. LCD right there. Then we clear it, and then we write character E. I don't know what, on the bottom. This is just writing onto the bottom to show how it's done that there. But the code for that is actually fairly messy. I'm not going to go through it. I will test it, make sure it works here. This is all the code for LCD delay. Here's our LCD 8 port that's how we would write to it right there. LCD 8 command, LCD 8. Somewhere here, there should be somewhere down here. There should be the LCD. Yeah, here's the LCD 4 commands right there. So there's our LCD command. These are all the functions that there. And basically, again, all they're doing is putting. There's the clear command 0 and 1. Set the cursor. Again, this is doing our writing to our so that there. So these are all the functions that basically, and this writes a char. This writes a string that simply all this. When we write string, what it basically does is it looks at the length of the string and goes through and writes one character at a time. And actually, it doesn't look at the length of the string. It looks for the null character. So this is the function that actually writes the character to that there. That sets the RS there. And this does our data transfer to do the other 4 bits right there. Right there. So this is our 4-bit shift right there. So there and right there. So these are all the functions that are required to write to the LCD. Again, I'm not going to go through and make you write those. These are available right there. Actually, this is in Notepad. But before I give them to you, I want to test them, because as I've noticed, my past experience is that every LCD display is a little different and tweaks are required. This is a tricky thing to get working. I've fought with it multiple times, because you buy something that says it's an HD 44780 interface, and you get it and you read the data sheet that comes with it, and you find that there's a gotcha somewhere. There's something that there. Every manufacturer is slightly different. I don't know why they can't get their act together, but that's there. So that's the LCD display right there. So really, at this point, I'm kind of at a loss where to go next, because this is where I would want to do a lab, and I don't have the parts yet. Right there. So I will probably talk next. I don't know where I'm at on time. Probably short on time. 45 minutes. I'm way short on time. Right there. Right there. Because the next thing I want to talk to about really is the analog to digital display, right, or the analog to digital converter right there. And it's fairly straightforward on setting the ADC. It's really very simple right there. Is that the analog digital converter, and we can do a lab on that. Actually, I didn't bring the board. Why don't I talk a few minutes about that, and I'll look at the board and see whether, because there's a potentiometer, as I recall, on our board. Let me look at our board. Yeah, we do have a potentiometer on port 1.2 right there. So we can go ahead and do that right there. So I think we will do a lab using the board and at least look at the potentiometer right there. So let me just spend a couple minutes. It's fairly straightforward. This thing is always a pain. Nope, that's not the right one. A textbook on ordinary differential equations. Yeah, this is the one. Okay. reading analog signals right there. This particular one lab right here, and we can use this almost the exact way it is. The only difference is we would change our port right there. Select AN0 mux output right there, right here. So our particular chip, if we bring up the, and right here it is. If we bring up the ADC right here, analog digital converters, enable ADC 0 right there, right here, and we want our ADC mux to be input. We want our port to be 1.2 and configure, and then we put port 1.2 as analog right here. This is in that that program that I talked about the other day, and it's called the configuration wizard right there. I would go into this right here, and I would say that I want to enable ADC 0 right there, and we want it to be in 8-bit mode right there, and we want it to start conversion on overflow 3 to run this particular command. Now, because we're going to put a breakpoint in so that we can see it right there. So we set this up right there. ADC 0 interrupt is enabled right there, which we don't necessarily have to wait for that enable it right there. Right here. So, and then I got to unplug that there so I can hit the OK. And this shows me my initialization for setting up my analog. This also shows that I'm using that port 1.2 as an analog, that initializer of ports. This enables my interrupt for interrupt 3. So this is our initialized device. We have to set up our analog digital converter right here. Right there. We're enabling it. There it's on pin 1.2. That sets up our mux. And that's a little bit different. You know, this sets up our timer. We still need to do this right here. That there. This is actually right there. ADC 0 is disabled. ADC conversions are initiated on overflow. Right, that there. We'll talk about that in a second here. Enable temperature sensor. This uses the temperature sensor on the chip. Right there. Select ADC 02. Again, ours is going to be a little bit different. Our interrupt routines. We have 2 interrupt routines right here. They should be there. Right here. Here's our timer 3 interrupt. You can see, and then our ADC 0 interrupt. So basically, what is happening in timer 3 is whenever timer 3 overflows, it clears it, but we've set up the ADC to automatically start a conversion on when we brought up our peripherals on our ADCs. Voltage reference. I just keep comparators. ADC, there it is. We set this there on a timer on timer 3 is when we so this will there. We could also write to ADC 0 busy a 1 to it, and then that will start the conversion. So we can either use timer 3 to do it, or we can do it manually. I was just writing a 1 to bit ADC 0 busy. You know, that's a bit addressable port in the special function register. So I think we will do. Let me write up a lab for when is our lab? Tomorrow? Wednesday? Okay, that gives me some time to after. What time is it? Wednesday at 10:15. Okay, I think I've got time put something together on that there. So let's go through and do an analog to digital conversion so we don't lose a week on the lab that's there. Because ultimately, I want to be able to have a digital thermostat that we can also program right there. So what, my next lab I would like to do is a keypad after that, where we press a key and we just see what key has been pressed. Then we add the LCD to it, so then we can that there, and then we add all three together, and that actually follows this particular example right here. That's hello world right there, but you see, that's just doing the count that there. That's just showing the count. I think there was a lab later on. There's the timer lab, which we'll go through the. We're just going to use the timer function as it is that there. Okay. This is her just very detailed discussion on the ADC. I'm just jumping right into it right there. So let me just stop at this point right there. So with a little bit of luck, I will go back to my office and put together something for Wednesday. That there. I've got 3 classes today. That's why if it was tomorrow, I might have a hard time. But I've only got 2 classes tomorrow, so I've got time to put something together. That there. So, okay. Let me now. I don't.